update on the problem. I've looked in my notes from a couple of years ago when I gave the same course, and well, the partial answer is collapsing the most recently attached cone in the first long exact sequence of spaces does not produce a sequence where all spaces are suspensions of one of these three. Why? Well, the reason is as is clear from the picture, at each place we get the suspension of the space three steps back, which we had 3 steps back, and let's recall the sequence. It starts with AX, so we do get sigma A, sigma X, but the next one will be will not be sigma of X by A. It will be sigma of X union cone of A, which is homotype equivalent but not exactly the same. And in order to construct an isomorphism between 1 star and 2 stars, we need to construct a ladder of the long exact sequences. Now, the signs are 3 pluses, 3 minuses, 3 pluses, 3 minuses, and so on. Okay, let's leave this. Let's leave this as an exercise. Well, at least we have a conjecture, which we can attempt to prove or disprove. Anyway, so the coming back to our problem of defining the to defining a cohomology theory, starting from an omega complex, an omega spectrum. So let's consider just this part of the long exact cofibration sequence. So in this part, every three-term piece is isomorphic to this one. So we have so we take this and apply apply the Hom in the Hom to Kn in the based homotopy sense. What do we get? We get Hn of sigma x goes to Hn of sigma A goes to Hn plus 1 of x by A goes to Hn plus 1, no, sorry, Hn of x. For the moment, we keep the n. Hn of x, Hn of A. Okay, so every three-term every three-term piece of this one is exact. Well, basically, by saying that this is exact, I mean that whenever I have two arrows which go one after another, the kernel of the second one is the image of the first one. Okay, now this Hn of sigma A by the suspension isomorphism has so let me write it here. We have Hn sigma x goes to Hn sigma A, and this is isomorphic to Hn minus 1 of x goes to h n minus 1 of a. Where in both cases the vertical maps are of the suspension isomorphisms and the horizontal ones are induced by the maps of spaces. So I can replace the first arrow where I have the sigmas by hn minus 1 without the sigmas. And the map is the same as the one induced by the inclusion x in A. No, A in x. So as a result, I get as a result, I get the exactness of the full long exact sequence of the homology groups. Not just this part, but also this one and this one. Does this make sense? So, starting from an omega spectrum, we constructed a homology theory. A reduced cohomology theory. By the way, if one is interested in non-reduced cohomology theory, I will not write the axioms, but I will just write this definition. So suppose I have a pair of spaces x comma a, where A is sufficiently nice, meaning it has it's closed and it has a subspace which deformation retracts, blah blah blah. Very well. Now I collapse A. I choose the resulting the point which we always get when we collapse anything as the base point. So I get a point in space x with A collapsed. I already know how to calculate the cohomology of this one, so I use this as the definition of the corresponding non-reduced homology theory. By the way, what happens if we collapse the empty set? Yes, so x so the formally when we collapse anything, we add an extra point, and identify all elements of whatever we collapse with the extra point. Well, if there is nothing to collapse, there is still the extra point. Okay. Well, let's firstly, are there any questions? Нет, получились какие-то кохомологии, которые мы построили по омега-спектру. Если омега-спектр, с которого мы начали, это Элленберг-Маклейн, то получится обычная кохомология. Если омега-спектр не Элленберг-Маклейн, ну тогда получится то, что получится. So the idea is that omega spectra make sense. Why? Because they give one non-reduced and reduced homology, cohomology theories on spaces. What to do with homology theories? We'll see later on. Homology theories, there is a way to construct homology theories from spectra, and most homology theories which occur in everyday life do come from spectra. Most, but not all. As for cohomology theories, they all come from spectra. And this is the Brown's representability theorem. Come from omega spectra, and again, this is a topic. I think this would make a good topic for a talk. So if you are interested, please let me know. Okay, now, apart from the co-vibration sequence, there is also the vibration sequence. Well, let's say something about it. So suppose So in the cofibration sequence, I started with a cofibration A inside X. So here I start with a self-vibration. And then despite the fact that the map P is already a vibration, I want to take not the fiber, but the cell fiber. Let's let's recall how exactly we replace a map by a vibration. Suppose we have an arbitrary continuous map, x to y. How to replace it with a vibration very simple. Instead of x, I take the space of all couples x comma gamma, where x is in x and gamma is a path in y, such that f of x is gamma of 0. And the map from x prime to y forgets the x component and forgets everything apart from the end point of the path, and this is what the map does. Very well. Let's do this for let's do this for P, and let's calculate the fiber of the resulting of the resulting map and the map from the fiber to E. Well, let's think. I want to apply this construction, but this time I want the gamma 1 I want to be the gamma. I want the gamma 1 to be. So what do we have? We have gamma 0 is P of E. Gamma 1, the base point. Okay. So what does this space remind you of? If anything. На что похоже вот, написанное пространство, если оно вообще на что-то похоже?
The path space of fiber.
The path space of the fiber.
No.
Okay, so it's a subspace of E and the path space of B, but moreover, we only consider paths which end at the base point. So, here, I instead of this condition, I can consider only the paths which end at the base point, and then this will be the only condition. So my claim is this is the pullback of the path loop vibration of B under the map F. Under the map P. So we have the path loop vibration on B, and we pull it back. We get the fiber FP, which is itself fibered which is itself fibered over E. How? Well, just by forgetting the gamma. And the fiber is the same as the fiber of this vibration. And the fiber of this vibration is omega b. Okay, so then we basically iterate this procedure. What does this mean? Well, this means so suppose we have constructed the space is fn plus 1 fn. Then I construct the next one as the pullback of the path loop vibration on Fn under this map. Then Fn plus 2 to Fn plus 1 is a vibration with fiber what? Yes, with fiber omega Fn. So, using this, we can do two things. Well, first of all, we construct a sequence of vibrations which is infinite to the left. And second of all, okay, I continue my sequence of vibrations from Fp. Let me call this I, Fi. I know that Fi is homotype equivalent to omega b. This is what we've just seen. Well, so I'm able to construct an arrow from omega b to f. How? Well, I first apply this homotype equivalence, then this map, then I return to f. Does this make sense? Okay, so and then we we use this to extend this this sequence to the left, where the map here will be omega b, omega I, and so on. And we run into the same sort of problem as with the cofibration sequence. There will be minuses. More precisely, there will be pluses and minuses alternately, which more precisely 3 pluses, 3 minuses, and so on, and so that first of all, in order to construct the second sequence, we only need this part of the first sequence, and then we want to prove that the first sequence is isomorphic to the second sequence. Where in the first sequence, starting from this place, I just apply omega to get the next map. And this almost works if we put in the signs. Okay, does the statement make sense? So exercise prove the statement, or there's a better way. There is a way to formally deduce the signs in the vibration sequence from the signs in the cofibration sequence, which is easier than proving everything from scratch. Okay, so basically for spaces, the vibration and cofibration sequences are different, but they're similar. What's the difference? Well, the first one goes indefinitely to the left, and the second one goes in the opposite direction. This is one difference. And also for spaces, vibrations and covibrations are not the same. Well, in a week or two, we will see an analog of all this for spectra, and we'll find out that for spectra, basically there's no difference between the vibration and cofibration sequences, and basically, both are particular cases of what turns out to be a distinguished triangle. Very well. Now we still have about quarter an hour. Let's calculate a few examples. We've defined a cohomology theory. Well, let's see if we can calculate the cohomology of anything. Well, apart from a point. Well, the cohomology of a point. So suppose we have suppose we have a reduced cohomology theory. Well, suppose I know the, no, not the point. The reduced cohomology of a point with respect to any cohomology theory is 0. So to get something more interesting, I need to take 2 points, which is the same as S naught. Okay, suppose I know the cohomology of S naught. Do I know, can I calculate the cohomology of anything? Well, I know the cohomology of the n sphere just by using the suspension isomorphism. I can calculate the cohomology of the wedges of spheres. Very well. Can I calculate the cohomology of the two torus as 1 cross S1? So, does it suffice to in order to calculate the cohomology of S1 cross S1, does it suffice to know the cohomology of a point, or do we need to know something extra? Let's think. So I have some reduced cohomology theory, and I want to calculate the cohomology of the two torus.
If A is two cycle torus.
Which one? Yes.
So it's one, which is one.
Yes. We have this long exact sequence, and what exactly do we get?
So yes, and so the torus factor S1 which is 1 is S2. Yes.
Okay, so
So it's sub X, I suppose.
yes. So one suggestion from Alexei was to consider the wedge of two circles embedded embedded in the two torus as shown in the picture. But then there's a problem. We have a long exact sequence. We know everything in this long exact sequence, but we do not know the maps, which is inconvenient because we don't have a way to compute those. But here is where retracts come to the rescue. So this is T2. Let me call this C. So if I take just one circle, not two circles, but just one circle, I will get a retract of the torus. And this means this means a lot. This means that the long exact sequence splits into three-term pieces, and every three-term piece has also splits, meaning the term in the middle is the direct sum of the other two. Does this make sense, or do I need to write this down? So in particular, Hn of the two torus is the same as Hn of C isomorphic plus Hn of T2 with C collapsed. Okay, so well, this is this one, and we know the cohomology of S1. In fact, we know the cohomology of all ascents. What about this one? Yes, so this thing is homotypic equivalent to S2 wedge S1. So we know the homology of S2. We know the cohomology. Sorry, we know the cohomology of S1, and we have the wedge axiom. We have the wedge axiom, which tells us the cohomology of the wedge is the direct sum. So the result is, so we have n plus 1 of S naught plus h n plus 1 of S naught plus h n plus 2 of S naught. So we have calculated the cohomology of the two torus for an arbitrary cohomology theory. And this is the answer. Okay, so inspired by this success, let's go one step further. Let's calculate the cohomology of the what? Let's calculate the cohomology of S2, which is the direct sum of two tori, meaning, in other words, a surface of genus 2. So this was the two torus. Now I have a surface of genus 2 and an arbitrary cohomology theory. And again, I want to calculate the cohomology of the surface using nothing but the cohomology of a point. Of course, this is not always possible, but let's see if it is possible for S2. So, are there any suggestions? In this example, retracts were very useful.
We can also take a circle here to get the wedges to talk.
Okay, so we can take the circle, but we need something to which would be simpler than the surface, and which would be a retract. So we need to retract the surface onto something simpler. Is there a way to do this? So here C was a retract, and here we need something else. Are there any suggestions? Want to find a simple subspace, but still not too simple, such that S2 would be such that this subspace would be a retract of S2. Not necessarily a deformation retract, just a retract. Wedge of two circles. Well, yes, but why? So, in fact, one can take one half of the surface and call it y. Now, there's a way to retract the surface onto y just by taking the reflection in the plane which cuts the surface into two halves. Very well. So y is a retract of S2. Well, here we needed to know the cohomology of y, but y is the same as a 2 torus minus a point, which is the same as S1 wedge S1. And so we know that the we know the cohomology of y by the wedge axiom. Now, what happens if I collapse y to a point? Well, I get the 2 torus. No, not Tn, T2. And so, the nth homology of S2 is the same as the nth homology of T2 plus the nth cohomology, sorry, it's always cohomology, of y. And as a result, I get, so the final answer is, well, I get n plus 1, okay, so I get 4 times h n plus 1 of S naught plus h n plus 2 S naught. Okay, exercise, generalize this to arbitrary genus. So it so happens that for surfaces, for orientable surfaces, in order to calculate the an arbitrary cohomology, the value of an arbitrary cohomology theory, We only need to know the cohomology of a point. Well, this is unfortunately this is not always like this, but for surfaces it works. And already for projective spaces it doesn't work. For real projective spaces. For complex projective spaces, probably too. Anyhow, are there any questions? Okay, well then this is it for today. I've run over time a little bit, and we'll continue next time.